So now I'd like to turn my attention to what happens if we have more than one source of a wave. How would those waves interfere? And while it is possible to think about transverse waves interfering, for instance, I can throw two pebbles into a pond and they will send out ripples from each of their sources and interfere with each other. I'm going to focus mostly on sound waves here. When you go into electricity and magnetism, since light is a transverse electromagnetic wave, you'll get to revisit that a bit at that point there. But let's think about sound waves. So the big idea here is that for me to have constructive interference, if I've got two sources of sound waves, so say I got a speaker here, and I've got myself another speaker here. Oops. Yeah, I tried. If I'm going to be listening to it, say over here, if I'm going to have constructive interference, I need the two waves to be doing the same thing at the same time. So let's make this one here red. I mean, they'll literally both be sound waves, so it doesn't, it's not like they have different colors or anything. It's just to tell them apart. And let's make this one, blue. So here, we've got it so that at all points, crest meets crest, trough meets trough, and so we'll have constructive interference. So what's going to matter here is what's the difference in distance between, say, this speaker here, speaker number 1, we'll call this distance D1, and speaker number 2 over here, we'll call this distance here D2. Well, for me to have the two waves doing the same thing at the same time, you can see here I had one extra wave front here. Obviously, if I could somehow magically put both of the speakers on top of each other, that would work too. Or say if I had the two speakers side to side and I was standing in the middle, they would be equidistant. I could also say have these differ by 2 wavelengths or 3 or 4. In any event, if it differs by an integer number of wavelengths, we'll end up with crest always meeting crest, trough always meeting trough, and having constructive interference. So this means that delta D, so my D2 minus my D1 here, will be equal to m lambda. Now here, in addition to m being 1, 2, 3, or 4, 0 is also a possibility. So this is just saying as long as the difference in distance is 0 wavelengths, 1 wavelength, 2 wavelengths, 3 wavelengths, whatever, that's going to work out to be constructive interference. All right, but let's say we wanted instead destructive interference. What would that look like? So here to have destructive interference, the big idea is going to be that we will want the crest and the trough, the crest of one to match up with the trough of the other. So again, let's make this one here red. So looking something like that. And let's go ahead and make this one blue. So you see here, I'm always got crest meeting trough, and so they'll always cancel out, and I will end up with destructive interference. So What's going to give rise to that? Well, on inspection here, this distance here is one loop. So that's half a wavelength. So again, if we say that this distance here is d1, let's move that there so I've got a little more room. There we go. And we'll say that this distance here is d2. Well, this is half a wavelength. That's certainly one possibility. It would be delta d would be half a wavelength. Can we think of any other possibilities? Sure. 1.5 wavelengths would give me the same difference. I'd still have a crest, mean, a trough, or 2.5, or 3.5, or 4.5, or whatever. So the general case will be m plus a half lambda, where again, we're permitting m to be 0, 1, 2, 3, and so forth. Okay, let's do an example of this just to make things a little more concrete for us here. So let's say you're listening to a pair of speakers. Whoops. And since this is physics land, you're listening to a beautiful rendition of the speakers playing a tuning fork playing concert A, which is 440 hertz. Now let's say that you are sitting some distance away from the left speaker for some reason. You're right in front of the left speaker. Let's make this distance 10 meters. Now, right here, unfortunately, your happiness turns to sadness when you realize that you can barely hear the concert A note, and you realize that you must be sitting at a destructive minimum. Let's assume that this is the first destructive minimum. And then let's figure out how far apart are these speakers to have created such a horrendous misfortune for you. Okay, so this distance here, from here to here, that's going to be our D1, which was our 10 meters. This distance here is D2, which we don't particularly know, but we do know that it is our d1 squared plus our x squared, take the square root. Now they gave us an important clue here. They said it's the first destructive minimum. So now you might be tempted to stick in a 1 for m, but don't. Look what the first possibility is. The first possibility is 0. So if this is the first destructive minimum, what we've got is that delta D, which is equal to D2 minus D1, is equal to m plus a half lambda, where m is 0 here. Well, we don't know the wavelength, but we were given the frequency. V equals f lambda, so lambda equals v over f. And since they didn't tell us anything different, we'll assume that it's the speed of sound at STP, 343 meters per second. All right, so following this thought through, we've got here D2 equals D1 squared plus, D2 is, the square root of D1 squared plus x squared. And we'll be subtracting our D1 here. And this will equal 1/2. And our lambda we said was V over F. So that's going to work out to be V over 2F. Okay. So let's go ahead and do a little bit of algebra here and see if we can't suss out what our x is going to be. So square root of d1 squared plus x squared will equal d1 plus v over 2f. We can square both sides. We'll get d1 squared plus x squared equals d1 plus v over 2f squared. And let's see, we can subtract d1 squared from both sides. And then finally take the square root. And if you want to do more algebra to make it prettier, knock yourself right out. But this will be good enough to get us the answer. So let's go and take a look. This is going to be, we said that our D1 was 10 meters. So 10 meters plus 343 meters per second over 2 times 440 hertz squared minus 10 meters squared. Take the root. All right, so now remember, 1 over seconds and hertz are the same difference, so that cancels. And our units check. That's good. So let's go ahead and grind that through on the calculator, shall we? So we will have 10, 343, 2 divide, 440 divide, plus squared 10 squared minus square root 2.82 meters. So I mean, that seems like a plausible distance that our speakers could possibly be separated by. Alrighty, in the next video we will be taking a look at beats. I'll catch you over there.